to us, and they see the motions of the stars. And of course, it's a little tricky because you can't measure transverse motion of stars. It's too small to see an effect. The transverse Doppler is booger all, but you measure the radial velocity. So first you take out, if these guys, galaxies like M31 and so on, they're not very far away, so you don't, redshift is not a big deal. Take out whatever translational motion of the overall galaxy, then you look at the velocities of the stars relative to their radial position in the galaxy. Of course, that works best for a galaxy that we're seeing that's pretty well tilted up. Doesn't work at all for one that's square onto you, right? But when it's tilted up, then you can get red shifts on one side and blue shifts on the other, and you plot the velocity as a function of position. And so indeed, people learned about that there was clearly much more mass there than was revealed by just counting stars and figuring out how much mass the stars should be, and therefore replacing the total mass of the stars by some point in the center of the galaxy and measuring the velocity of those guys and figuring out how fast they're winding around. So I can do that with just 1 over, just the potential 1 over V, 1 over R. But for the ensemble, I can use directions. I can use the velocities going in any old direction by using the virial theorem.
It's interesting you get the wrong answer for that. It's kind of like the neutrino problem you mentioned. You use the Gauss's law version, and then it comes out.
But in this case, it comes out dramatically wrong. At first, I presume you all know about the first evidence for dark matter was back with Fred Zwicky in the 30s and so on, when they started doing this and go, what the hell's going on here? And of course, early on, as with the Hubble flow, people didn't trust their measurements very much. And it took some time for the problem to mature and didn't become a serious issue really until just a couple of decades ago. And became just inescapable that something is very, very wrong and missing. And as you will hear in various talks at the colloquia and so on, people are still trying to sort it out. For a long while, there was a period where people were trying to say, well, maybe it's just gas that we haven't taken account of. There's a lot of damn gas out there, and dust, and maybe Jupiters, maybe small black holes. Some people still argue about that. But the answer is that it's off by 2 orders of magnitude for big clusters of galaxies. We wouldn't have discovered it if it were a few % effect. It's a huge effect. There's something really missing. Now, in the context of our course here, somebody is likely to say, well, maybe it's this 1 over r squared assumption that you're making for all of this that's wrong. And so a whole industry for many years has been of people trying to construct theories which are post-Newtonian or non-Newtonian, that are some moderation of general relativity, or putting in the simplistic ways, putting in some other term along with 1 over r squared. Suppose it's power law expansion or something. Can I get away with it? And the answer is that people still struggle with it, and there are advocates of non-Newtonian forces. We don't want to get into this now, but
You're talking like modified gravity.
yeah. But there are some so stellar examples. Everybody shows a plot when you go to the colloquia. Somebody's talking about dark matter, they'll show a plot of the bullet cluster of colliding galaxies, and where it seems pretty hard to escape of that. There seems to be some unseen matter that went along with the cluster of stars, but not with the gas, and that there's something else there. Although I've seen claims by these, by the advocates of these modified gravity theories that they can explain it, although I cannot explain how they can explain it. I've heard the story, but I can't reproduce it. So at any rate, this is great stuff. This all connects to some frontline physics issues that you may recall also. There have been a couple of spacecraft, the Pioneer spacecraft, and including the Galileo probe recently. But the Galileo spacecraft, Pioneer probes have been out there for what, 30, 40 years, some long time.
Pioneer ones, those are the Saturn ones?
Mhm.
Those are the Saturn ones, the ones that passed Saturn and then just got shot out?
They went, yeah, they're on the way well out of the solar system now. Their velocities were not quite tracking with what people thought they should be. But now I understand the commonly accepted wisdom is that the difference in velocities had to do with some escaping gases from they modeled up the spacecraft, and sun heating on one side and liberating some gases, giving a little, absolutely microscopic acceleration, and enough to be more than the solar radiation, but that seems to be not something that people are believing, that there's some variation in gravity that we can measure at the solar system. It turns out that these modified gravity theories, that a good testing regime for them turns out to be not on the grand scale, but we can do tests on the solar system scale, and those are very constraining because they're very precise. The stuff on the grand scale would be constraining if we had very precise measurements, but we don't. And so for Browns-Dickey theories and so on, which you will learn about them if you take general relativity, they're pretty well pinned down. There's not a big phase space for escaping. And the solar system measurements are very good for that. So, okay, moving on through following the text in here. The next thing that he introduces is a lovely trick, which is for the one-dimensional case to make the change of variables in his terms to u is equal to 1 over r, and just change the integral around by 1 over r. And this is such a lovely trick, and it leads to simplification of the form, as you have seen. But I just want to impress you that is not a one-off trick for this situation. It turns out that this trick works in other circumstances. You'll see it in E&M as well. Have you seen this game in E&M? Huh?
And even in quantum mechanics, where you're just solving the Laplacians with first spherical coordinates.
Right.
You could also make an argument for one of the problems in the homework set earlier in the semester, where we had a force that had terms like 1 over r squared and 1 over r. You could probably do something with that too.
Right. And it has to do in a deep way with topology, which I don't know enough mathematics to say what's going on there, but there's certainly a great trick, especially in E&M. There's some problems that you can solve just trivially if you flip the coordinate geometry over by 1 over, get the solution right away and flip it back. So there's a correspondence between a set of solutions. Right. So in setting it up, you then see that the statement here is the orbit is therefore invariant under reflection about the apsidal vectors. And the apsides are the extremal vectors to the near point and the far point. And or if it's not a 1 over r squared, then at least the extremal points. Yeah, I guess that's. So then he goes through this business of writing down the solution in terms of the angle, which again, you have an equation that has this nasty integral on the bottom. These kinds of, whenever you see these guys, you can bet that there's elliptical functions lurking in the neighborhood. If you're lucky, they'll turn out to be trigonometric. But if you're unlucky, they'll turn out to be elliptic functions. Or if you're really unlucky, they'll turn out to be something worse. I don't know if you guys have run across the confluent hypergeometric function, one of my old favorites. This is a perfectly horrible function, but it fits almost anything. If you're at your wit's end, then probably the confluent hypergeometric function will fit it. It's a totally useless function because it's just one of these functions with a lot of indices, and you have no clue as to what the damn thing looks like, and then you go look up in Abramovitz and Stegun and look up approximations, or nowadays you get some computer program that'll tell you how it varies. But it's really, it's one of those things, well, okay, I got a solution in the confluent hypergeometric function, but it didn't do me much good. Except, of course, I can have a subroutine on my cell phone probably that calculates it these days. But there is something really, really special about the sines and cosines, right? These are the functions that, the exponential e to the x is a really special function. A beautiful, simple function, and the sines and cosines are just the alternate terms in the series expansion of it. They are something really simple and unique, whereas some of these other buggers, the Hankel functions and the Bessel functions and so on, although you can make simplifications for small parameters and so on, in general they're quite a mess and don't lead to much insight unless you're a great wizard at them. Okay, so he makes the point here that with this, that you get the simple functions only in the cases of the power law r to the n equal +1, -2, and -3. Some deep statements of topology, and damned if I know what they really mean. And that the elliptic functions only for +5, +3, 0, -4, -5, and -7. Oh yeah, you would have guessed that.
Did he just try a whole bunch and see which ones actually worked out?
Oh no, I'm sure he didn't do anything. People over the years have struggled with this. I'm sure you'll find mathematical papers where people labored over it.
Sure. You read a 10-page paper and at the end they'll say, and therefore n has to be -7.
At any rate, so what one does in the real world is numerical integration for these sort of things. But I want to maybe point in time for a little mention of numerical integration, which is great fun. You can write a program without too much trouble to move these things around. But you can also get the wrong answer very easily, even with the very fancy programs where people have numerical integration for the orbits of the planets and so on. And this, we touch on the sensitivity to initial conditions business. I'm sorry, I've asked this before, did everybody have a little bit of chaos theory in your undergraduate?
Yeah, not me personally.
No.
A little bit.
Just
Okay.
A little
Well,
bit in
There are some very, very nice things that you can be quantitative about, and one of them that turns out you can be quantitative about is the sensitivity to initial conditions. And that in many systems, particularly some systems that are getting close to the chaotic regime, and we will talk about, I think we'll talk about a little later, the driven damped oscillator, which is kind of the simplest system around. At any rate, if you calculate forward in this, you get yourself into trouble pretty fast. And suppose I start at 2 calculational points separated by just a small amount in pick something, the initial position vector or whatever, and march it forward in time. The phase, suppose it's some periodic or quasi-periodic motion, the phase will start to walk away, and it walks away exponentially. So that's what people mean by SIC, sensitivity to initial conditions, that the phase walks away exponentially. And it can be a real bitch. It can be, you know, the thing is out well away from where you expect it to be in just a few orbits when you're sitting near these unstable points. But in practice, for instance, calculating, you see these things in a planetarium where they'll run the planets back to, you know, when Christ was born, here's where the stars were and so on. Well, that's not so easy. Because running the planets back, you have to have had all the planets exactly right, and you have SIC going on. I'm not sure how bad it is, but it's pretty bad. There was a point that I wanted to make here. Oh, it's coming up here. I'll come back to that in a moment. Okay, there was the Bertrand's theorem. So there's some more stuff about what orbits can be closed. Obviously, if you start fooling around with the power law, then you can get orbits that are not closed, right? My ellipse, if I just diddle 1 over r squared a little tiny bit, then, and I'm in an elliptical orbit, then it won't close. It'll come back and it'll start to make a flower pattern. And that's in point of fact just exactly what happens with, if you get in close enough, the GR corrections are starting to matter on the inside, then the perihelion will wander about. And in fact, it's another topological statement that I don't really know why it is, but it's the way it is. The only central forces that result in closed orbits for all bound particles are the inverse square law and Hooke's law. Full stop. Why is that the case? Something marvelous and magical about the geometry of space or physics. Could it be different in a different universe? Could be different in a different universe if we had a very different metric or some such thing, but in another set of dimensions. I'm sure you can get yourself in trouble with that. Okay, so then there's Kepler's starts discussing the inverse square law of force in terms of the Kepler formulation in terms of the eccentricity. And again, you will see these people talk about the eccentricity of the orbit. That's a fairly common description. So if the eccentricity is greater than 1 and the energy, total energy is greater than 1, then the orbit is not contained and it's a hyperbola. For that one special case where the ellipticity is equal to 1, the energy is exactly 0. And notice the energy here we're talking about is the energy at infinity, right? Where we made a definition of the, because you can freely add a constant to the, or subtract a constant to the energy to call it whatever the hell you want. The scale you can fix, and the 0 point you are free to fix, has no effect on the equations of motion. And although note when I say that you're free to fix the scale, you can fix the units, but when you fix the units, you got to fix them all. So you, in other words, the gravitational constant has to be kept relative to the masses. So I can adjust what I call these units, but relative to each other, they have to remain the same, as we've talked about. The Lagrangian is independent. We can multiply the Lagrangian by some constant, but we got to multiply the whole damn thing. That includes 1/2 mv squared and the potential energy piece. But I can't change one relative to the other, because that will have effects on the dynamics. Okay, so the special case is the parabola, and the next, then the case of epsilon less than 1, the ellipse, and epsilon, or he writes it as E, people often write it as epsilon, E equals 0 is the circle case, where the energy is in k squared over L squared, k being the gravitational coupling constant. So blah, 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 blah. Here, where do we start this discussion about the, well, okay, so you can write the orbital equation with the time taken out in some nice little form, like in 364, a times 1 minus the eccentricity squared divided by 1 plus epsilon times cosine of an angle. Nice simple formula. So, or it looks like an ellipse when you write it r times cosine theta plus something. That beautiful simple form. Okay, the thing that's interesting, if you want to have some fun, take some time, of course, in astronomy, where they talk about how they actually do the measurements, and the geometry can be just terrifically complicated. As you can imagine, I make a few observations on the sky, and how do I turn those few observations on the sky, where I've measured some coordinates relative to my telescope at this time, at this point in this season, into some stellar coordinates, and I turn that into an orbit. It's not easy. So here, finally he gets around to talking about on page 99, the anomaly. You'll hear the astronomers talking a lot about anomalies. That's their traces back to classical astronomy people. The anomaly is simply the difference between what you would expect if you think that the, say that